to all of astronomers. I'll try to talk a little bit about that, but I'm not sure I'll have the time. So, okay, so that's what the Hubble law is. V equals hd. V is this vertical, the position on that vertical axis. D is just, there's D, just how far out it is. And this is what's called the Hubble constant. It's just a number, and it tells us if you know V, you can simply divide V by h, which we know, and you will find the distance to that particular galaxy, just what I've been saying in this. So that's just that, and it's because it's a straight line. Okay? Question, anybody else? Yes?
Since we're in a galaxy and we're observing another galaxy,
yes.
It's hard to imagine that we aren't stationary.
Okay. Tough question.
Yeah, and how do you know how fast we're going relative to the other galaxies or star?
The short answer to that question is that the only thing we can do, because we're the only ones making the measurement, is to say what we're measuring is with respect to us, relative to us. Okay, and it turns out that that's the right way to say it. From Einstein's theory of relativity in 1905, 1915, both of those years, he provided convincing arguments that any observer, it's relative to any observer. So there's no place that you could go and say, well, I really should be over 2 million light years in that direction and measuring it over at some place like that. Every observer should see the same thing. More about that in a minute. Let me add a little bit to your question that you probably weren't thinking about. But remember, we also move within our own galaxy. We have a 250 kilometer per second speed going around. So we have to take into account that speed to fix that. And that's built into all of the points that you see up there. Okay. Let me just give a quick example, and you can see what this is. I've got a couple of shots of a galaxy. M87 is a relatively nearby one. We look at M87 in the spring every year. It's a beautiful, fuzzy little patch in the spring sky. 55 million light years from us, moving at 1,000 kilometers a second, something like that. Okay? And if you look at another galaxy, and here's another one, and what we're looking at is this fuzzy little one here, but it could just as well be, this is a whole cluster of galaxies. And you can see that what is a fairly large galaxy there, this other one is we're going to presume that it's the same brightness and the same size as M87, but we're seeing it, and it's a much smaller little point. We would infer that this is a more distant galaxy, and we'd be right, and we've actually measured the distance to it. Corona Borealis cluster, instead of being 55 million light years from us, 1,100 million light years from us, a billion light years away, and it's moving way, way faster. And this is the kind of thing the Hubble law has successfully found. You can look at a bunch of examples. There's M87 right there, but now we're looking at the galaxy, its relative size to other galaxies that are going to appear down here, and we're also looking at the spectrum. And we're looking at the two little twin pair lines right there that are made by calcium. I pointed those out before. And that's where we see them for M87. If we look at Ursa Major galaxy, it's further away. We can tell that by the fact that it's dimmer and smaller. And look at this. Okay, now this is the color red is over here. The color blue is in here. So if this were colored instead of a black and white image, astronomers only work in black and white images, so I'm sorry I don't have a colored image of this. But you can see that that pair is to the right of where it should be. And why is that? Because the wavelengths are stretched out, and stretching out the wavelengths is exactly the same thing as saying that the color of those two lines is off to the red side, to the right-hand side. We'll look at a couple more distant galaxies. You can see this is a succession of fainter and fainter little dots, further and further away, and you can see that those pair of lines gets further and further. Those are lines that are blue right there. But in here, the lines, that's the red part of the spectrum. They have been shifted clear over to the right. You almost wouldn't even recognize them. And that's a real issue. And all of these lines used to be in the ultraviolet part of the spectrum. They've come into the visible part because of the speed of these galaxies. Let me tell you something. This is important. That means the light has been shifted to the right. You're going to start to hear about the James Webb Space Telescope. It's going to be launched in 2020, I hope. And James Webb is designed to be able to look at infrared light more than red light for exactly this reason. Oh, a few other reasons as well, but it's because for the distant galaxies, most of the light has been shifted to the red. So we ought to build telescopes that want to look at these distant galaxies that are designed to be more sensitive to the red part of the spectrum, and that's exactly what you're going to be hearing about when you hear about James Webb. Okay, so there's a quick summary of the way this works. I want to now change the emphasis here. We've been talking about what you see with the Hubble law. And we've been talking about how you can use the Hubble law without understanding it, just to say, okay, I can find the distance to a galaxy by measuring its speed. But now what we want to do is what people immediately started. As soon as Hubble published this in 1929 and in the years following it, people wanted to understand what this really meant, what it amounted to. And you've heard this many times, and let me just talk a little bit about it. The idea is that this is the way we see this law, that is galaxies all receding from us, is exactly what we would see if the universe were a expanding and growing universe. And the way we mostly talk about that is to make analogies. And I want to make an analogy right now. I'm going to do this with the understanding that this is an analogy, and it may, you have to take the analogy as a teaching way to get across the idea of what this expansion is and why we think it's an expansion. But you have to remember that this is an analogy. The way we almost always start by doing this is to say, imagine that the universe is the surface of a balloon, okay? And what we see when we look at the Hubble law is an important aspect of what was on that last graph. The graph is made by looking at galaxies in any direction in the sky. We weren't just looking in one direction. And Slipher was looking in all directions. Hubble was looking in all directions. We do that now. Every galaxy that's far away from us has a higher velocity than the nearby ones, no matter what direction you look. Okay, crucial idea. It's not just in one direction. It's everywhere. Okay, you all with me on that? So how do we explain that? We explain that by saying, imagine that this is the universe, and I'm going to put a bunch of dots on this balloon with a pen. Can you also, I'm kind of in, is this, okay, you can kind of see that. And then I'm going to imagine that an ant, there's a bunch of family of ants on this balloon, and an ant rides on each dot, and we are represented by ant A, that's right there, okay? And there's another ant here, and that represents other galaxies. And so as this expands, as I blow up the balloon, those dots move away from each other. And there is no dot on this surface that is going toward any one of them. So an expansion will look to ants riding on a balloon exactly like the Hubble law. It'll be a Hubble law. And you can, that's, now one of the things that's a little wrong with this analogy is that if you look carefully at my dots, I put a dot with a pen on this, and so the dot kind of grows too. But in the universe, gravity holds the stars in the galaxy together. It doesn't allow the distance within a galaxy to increase. Only the distance between galaxies. Here I am on that. My ant is right there. This ant has got that much rubber between. And so he moves at a speed of, 1/10 of an inch per second or something, okay? This one, the guy that's over here, has got twice as much rubber here. So there's twice as much rubber growing. He's going to move at twice the speed. Exactly the way the Hubble law works. If you're 5 times as far away, as one galaxy is 5 times further away than another one, that more distant galaxy will have a speed that's 5 times as great. V equals hd, you just put d 5 times bigger, and you find the velocity that is 5 times larger. So that's a factor from the way the straight line law works. Everybody with me on this? So now the problem with this is that the universe is expanding in 3 dimensions. This is a 2-dimensional analogy. Okay, so we have to limit ourselves to being on the surface of this balloon. There's no center to it. You know, so it can be confusing if you take the analogy to be, you know, the gospel truth. Okay, you've got to accept that this is an analogy in 2 dimensions. I've got a 3-dimensional analogy that you can think about, and that's in the picture that's up there. We can just leave the lights, you know, for now. Picture up there is a picture of a jungle gym, which is a 3-dimensional structure. You can imagine that every place where the arms cross, you put a galaxy. And then you build into each arm a little electric motor that you turn on and it cranks away and it extends the arm. So if you're 2 junctions, 2 arms away from the home galaxy, you'll be moving twice as fast. So it's a whole, and it's true in all directions. The problem is that we've never seen a jungle gym that extends in all directions and has no limit. So it's an infinite 3-dimensional jungle gym analogy built out of little electric motors in every arm. So it's a little bit stretching. But it's an analogy that catches something that this doesn't catch. That catches the 3-dimensional nature of this. Who's got a question about this? Yes?
When you were doing the analogy with the balloon, this is one of the things that just causes me to get lost with discussing the subject, because there's so much talk about space expanding.
Yes.
And, you know, space is being created between these galaxies, and they're not really moving. It's just that space is being created between them, and that just seems to be so ridiculous that I can't grasp it. Why can't the galaxy just move?
Yeah, you know, a lot of that is exactly the words that we choose to describe this situation. And all a scientist would say is, all I can measure is a recession velocity. And so we don't call it anything else except that. But then in trying to explain it, we say, well, the empty space expands. And there we're getting into what you picked up on, which is a really mind-boggling part of this. One of the reasons that I love talking about cosmology, because it is really, really hard to visualize. That's why we're here, okay? We're here to deal with these really tough conceptual things. I think that's why we all study astronomy, is to deal with these really large distances and really ancient stars and really incomprehensible things like the expansion of empty space, which so that's really one of the reasons I wanted to talk about this tonight, and let me get to my next slide, because it'll kind of begin to get into this. How much time do I have, Roger? Tell me when I should stop.
How long you want?
Oh no, I can't have all of it one, because you guys will still be here.
We normally go 45 minutes to an hour.
Okay, so if I stopped in 15 minutes, is that okay?
Fine with me.
Okay, okay. I don't want to go on too long.
I got a picture.
Okay, so how do we understand this? And this is here's one of the places where I find students have a lot of trouble in this, and everybody does. Most people think that describing the Hubble law and the expansion is really describing the analogies. The rubber balloon analogy, the jungle gym analogy, whatever other analogies you come up with. And that turns out to be missing the huge part of this, and that is the theory that describes it, you know, in a mathematical way. And here's what it is. It's the the theory that comes from those